It's Facebook. That is Periscope just going live. Twitch is up. And YouTube is up. We are now everywhere across half the planet, or something like that anyway. Right. Good evening and welcome to Cafe Sci. I'm James Bohr, which some of you already know, and I will be hosting you for the evening in this Cafe Sci. I'm being a little more organised and possibly formal because it's now been just over a year since we started and brought this online. So a bit about Cafe Sci. It's an open science movement promoting conversation and discussions, particularly discussions and conversation rather than education, about scientific topics outside of your normal formal academic lecture. So just over a year ago, when the first lockdown was coming in, I worked with Chris, who's our speaker tonight, and my dad, conveniently, to bring the Cafe Scientifique that he had set up in Woking about 8 years ago now, 9 years ago, online. There were a number of speakers lined up already, and giving in to just cancelling the events didn't seem quite right, particularly at a moment when scientific understanding, conversation and literacy was as important as it was at that time, and still is. So since then, we've had over 30 talks on a variety of different scientific topics, various degrees of scientific. We always say science is what we say it is, from speakers all across the world. And moving to Cyber Cafe Sci from a physical one has given us opportunities that we just wouldn't have had in a purely real physical space, even at the art gallery or the wine bar. We're not going to be going anywhere anytime soon. We're going to keep this running, and we hope that you'll continue joining us on events in the future, as we have some quite exciting ideas about where to go and how to enhance the experience and build more of the community around it. Now, with all of that said, I'd like to introduce the founder of Woking Cafe Sci, and therefore the godfather of Cyber Cafe Scientifique, talking about his endless and apparently futile quest to spot cosmic rays in a pint of beer, or I'm told it could also work with Prosecco, Dr. Chris Bohr. His doctoral studies were all in magnetic imagery, but we're not going to talk about that. What's more relevant is that he worked at CERN for a year, which laid the serendipitous seed, which would eventually brew, and sorry for the pun there, into this journey of attempted discovery through beer. If you have any questions, please put them in the Q&A box if you are in our luxury Zoom studio, the chat box, or if you're watching on the live stream, post them as a comment on whichever stream you're watching, and I'll collect them and forward them to Chris to deal with at the end. If you're watching the recorded session, I'm afraid you're out of luck. We haven't mastered seeing into the future yet, but you can always come along to the next live session. Without further ado, take it away, Chris.
Thank you very much. Okay, I'm going to just set myself up here. Right, from the beginning. And let's see if I can do the correct things on. There we go. James, tell me that you can see my slides now. Yes?
Yep, they're visible, and
good.
The captions as well.
Perfect. All right. If I get lost, it's because this is very complex, or it's complex as a talk. It's not complex as a subject. It's just actually quite easy, really. If you need a good reason to have one more beer, I'm hoping I can help you to see the science in it. It should work, as James said, just as well with Prosecco or even sparkling water, but I'm going to leave it to others to test that theory. Sometimes you might see something that is incredibly rare. If you do, you might find it hard to convince people that you really did see it. Even if people do believe you, they might still dismiss you as anecdotal, meaning unscientific. Or maybe you might set out to see something rare but you don't see it. And does that prove that the rare thing doesn't exist? There is a thing in science called the black swan. If I say there are black swans, you can't prove that there aren't. It was a Roman historian called Juvenal who came up with this idea, and being a misogynist, he was talking about trying to find an ideal wife and saying they didn't exist. At that time, nobody knew there were black swans because nobody had seen them. But when people discovered, when I say nobody, I mean nobody in Western civilization. When Western civilization discovered Australia, the place was full of black swans. And in fact, the black swan is now part of the coat of arms of Western Australia, I think, showing how very special they are. The idea is, if I say there are black swans, you can't prove there aren't, because you can't prove a negative. But if I see even just one black swan, then I am proved right. They do exist, and nothing you can do can prove they don't. Unless you say that my black swan is anecdotal. Twitter has a thing called pictures or it didn't happen. It's a way of dismissing people's personal stories. You know, somebody saw something extraordinary or saw somebody do something extraordinary. Pictures or it didn't happen is a way of saying it didn't happen. I don't know what people did to prove things when we didn't have cameras. And I have some sympathy with it because I love the motto of the Royal Society, which is take no one's word for it. They used to insist on meeting to verify by experiment and demonstration and seeing with their own eyes what anyone said. It's a foundation of science. It's reproducibility. But what if the thing you're looking at is really rare? This is a Brocken spectre. The Brocken is a mountain in the Harzburg range in Germany. This one was photographed by Andy Leader in the North Yorkshire Moors. The spectre is the shadow. The halo around the shadow's head is called a glory. The sun scattered by mist. It's a sort of rainbow. Scotland's a good place to see Brocken spectres, obviously, because of all the Scotch mist. Charles Wilson worked at the observatory on Ben Nevis and became fascinated by glories and mist and clouds. He wanted to study these things, how clouds form, as well as how light is scattered in them, and he designed a machine in which he could create clouds. That machine is now called a Wilson cloud chamber. Wilson recognized that mist, and so probably also clouds, form when water condenses out of the air. And we all know that if you reduce the pressure, the air gets colder. That's the gas laws at school, PV equals RT, Boyle's law. Maybe you don't remember it. So Wilson's machine had a sort of piston with which you could decompress the air in a glass globe, reducing its pressure and letting any water vapor condense out. This was a way of making a cloud in the laboratory. You can make a mini cloud chamber by opening a bottle of beer. If you look in the top, as you open it, you might see a little puff of mist, and I'm going to try and do that experiment here. It often doesn't work because it depends on the temperature of all sorts of things. Right, so that doesn't like me. Go. Here we go. Demonstrating how to open a bottle of beer. I've got Beck's and I've got Bavaria here. Beck's is better for the experiment because it doesn't produce too many bubbles. Bavaria is a nicer beer. They're both zero alcohol because I'm on a professional stand at the moment. As I open it, you might have seen a tiny puff of mist. If you didn't, there's no problem. Do the experiment for yourself and do it enough times until you do actually see the little puff of mist. That's like Wilson's cloud chamber. It's the air expanding and cooling, and so the water condenses. It's like cold steam. In fact, we'll see that it's very like cold steam, although totally unlike it too. It's intriguing now to be reminded that at the time, this was revolutionary. The idea that one should construct an artificial environment to study nature, a controlled experiment, was quite controversial. At the time, it was more common to think that if you wanted to study nature, you should go out and observe it, not make some artificial copy of it. Now we almost automatically think the opposite. In science, we crave the controlled experiment, and we dismiss the anecdotal observation. We've moved a long way from the idea of the natural sciences, observing nature, and towards a controlled laboratory science. So unraveling this modern way of doing science, taking it back sometimes to observing nature, is one of the themes that led me to start the serendipitous beer bubble chamber cosmic ray detector experiment. The cloud chamber demonstrates something odd about clouds. As air cools, so water condenses out as mist or clouds, or as dew, which forms on surfaces such as leaves or grass. The temperature at which water starts to condense is called the dew point. It's not the mist point or the cloud point or the condensation point, and there is a reason for its name. We can work out when water will start to condense by something called the partial pressure of the vapor. The more water vapor in the air, the higher the dew point. We know that because it's obvious. On a hot, humid day, it may feel wetter than a cold, dry one. The more humid the air, the wetter it feels. But water doesn't condense out of the air at the dew point. You can cool air way below that point, and still the water won't condense. This is called supercooling. The air is cold enough that water should condense, but it doesn't, except as dew on surfaces. Water needs something on which to condense, to trigger it coalescing into droplets. Water, by the way, is absolutely, totally weird, but that is another talk entirely. Here's a curious thing. If you form cloud in a Wilson cloud chamber, then let the droplets evaporate, you can cycle it again to make a new cloud. But if you keep doing this, eventually no cloud forms until you let in fresh air. Because the cloud needs something on which to condense, dust or charged ions. Air that is truly clean, clouds don't form in so easily. That actually happens in our atmosphere as well. Certain types of algae emit a sort of sulfurous particles above the ocean, and that's a necessary part of cloud formation. And interestingly, although again subject of another talk entirely, cosmic rays play a very small role also in forming clouds by causing them to nucleate out. We see this most commonly in vapor trails. They're like a cloud that forms where an aircraft passes, triggering the condensation by disturbing the air or by its very presence. And what Wilson found was that cosmic rays passing through his cloud chamber triggered vapor trails. So he could literally see cosmic rays passing through his cloud chamber. And interestingly, if you Google cloud chamber pictures, all you'll find are pictures of cosmic ray tracks, not of clouds, because that's what the cloud chamber became used for. Our sun at the moment makes mostly helium. It fuses hydrogen into helium. It's called the proton-proton process. It isn't that simple. You can't just smash 4 hydrogens to make 1 helium, because you can't get them all close enough together at the same time, even in the crushed interior of the sun. So you have to do it in steps, a chain reaction, 1 collision of 2 particles at a time. On the left, I show that chain occurring, so 2 hydrogens combine to produce a hydrogen 2 or deuterium, and then that combines with another hydrogen to make helium, 2 protons and a neutron, and then that combines with another helium. So the reactions occurring in the sun are not the simple thing that we expect, which is 2 hydrogens combined to form a helium. They're much, much more complex than that. And they rely on a chain, but in that simple chain, only helium is produced. So our sun has hydrogen and it makes helium. On the right, I show another process that relies on having some carbon and nitrogen and oxygen to seed the process. That's some stardust in the new star, but that also produces only helium as its output, although it requires the carbon and oxygen in it. The solar wind is a wash of particles that are thrown out of our sun, and you see that in the top picture there as the corona. Almost all of it is hydrogen, protons, or electrons, which are even lighter, with a bit of helium and a tiny amount of other things like carbon and oxygen and iron that were actually seeded into our sun from other stars in the dust and gas from which it was formed. Protons are tiny, helium only 4 times as big. But cosmic rays come quite literally from the cosmos, from outside our solar system, often from beyond our galaxy. They are incredibly energetic, fast-moving particles ejected from stars, including massive heavy particles that can only be formed in stars incredibly more massive than our sun. Novae, supernovae, other kinds of cataclysmic galactic events that are necessary to create the energies to form those heavy particles. Cosmic rays have energies that far exceed even what we can make in our biggest and fastest particle accelerators. To make heavy elements, you need a much bigger star than our sun, huge, in fact, or an exploding star, a supernova. A supernova can make iron and even heavier elements. And iron is like the sync process of nuclear fusion. It's kind of what you end up with, the easiest thing to finally make. And so there's a lot of iron in the universe. The processes involved are incredibly complex, as you see from the chain below. They're based on rare, random chances. So it's incredibly unlikely that this would ever occur. But if you're in an environment of such crushing density in the midst of a supernova, even such occurrences can become common enough that they actually happen quite often. In fact, it's interesting that we now know that we don't know where cosmic rays come from. There are too many of them, and they don't come from where we think they should. But we do know they are incredibly energetic, fast-moving particles that have traveled across the cosmos to get here, often at nearly the speed of light. And these are what Wilson saw in his cloud chamber. The Crab Nebula is the picture I'm showing there. That's the remains of a supernova, an exploding star. Even its light takes nearly 6,000 years to get here. The fastest cosmic rays go a bit slower than light, and so they take a bit longer. So the cosmic rays have been in outer space for 6,000 years before they reach us from that. Cosmic rays travel for thousands, millions, sometimes billions of years. They're incredibly dangerous. Living unprotected in space would be like having a full body X-ray CT scan every week, all of your life. Cosmic ray, they travel millions, sometimes billions of years, because it's traveling at close to, but not more than, the speed of light from its original birth in the massive explosion. When it hits our atmosphere, its energy is such that it creates a tiny nuclear explosion. It and whatever it hit shatter into exotic, strange particles, pions, which are like broken up protons. But pions are unstable, so they disintegrate spontaneously into muons. And muons are really weird, but very common. They're heavy electrons, about 300 times heavier than any electron, but much, much lighter than a proton. But they're otherwise quite similar. I became interested in muons during my undergraduate years because I did a project with Professor Daphne Jackson at the University of Surrey to find weird quantum chemistry when a muon knocked an electron out of an atom and then formed a tiny atom with an incredibly heavy electron, and then that combined in a chemical reaction to form a really weird molecule, a muonic molecule. That was my first practical confrontation with the collision between particle physics, where everything is particles, weird particles certainly, but easily visualized as tiny billiard balls flying through space and hitting each other, and quantum mechanics, where nothing is real and only abstract mathematics can even begin to model what we observe. It's like from the sublime to the ridiculous, because the particle physics is so easy to understand and the quantum mechanics absolutely impossible, but both are necessary to understand the phenomena that we see. Muons are also unstable, but they live longer than they should for an interesting reason. We all know about relativity, and if you travel very fast, time goes slowly for you. Muons are formed in the upper reaches of our atmosphere by the primary cosmic ray. That creates a cascade of pions that soon disintegrate into these muons. There are many, many, many muons, and they're often traveling at close to the speed of light. We all know about relativity. If you travel at the speed of light, time stops. If you travel very, very fast, time goes slowly for you. And muons travel at close to the speed of light, so time almost stands still for them. At light speed, in a non-relativistic world, a muon would travel a few hundred meters before it disintegrated, high up in the outer atmosphere. But they don't, because time stands almost still for them. Time goes slow enough, in fact, that they can travel kilometers, and so they reach the ground. By doing so, muons help prove relativity because they're like fast-moving clocks. And they reach the ground, so make up most of the cosmic rays that end up near us. But if they hit something, like their original great-grandparent cosmic ray, they explode because they stop. So time no longer stands still, and they die. But before they die, if we're lucky, they may leave a trail of destruction that tells us they were there. There's probably a muon passing through a pint of beer every second or so. They are that common. So where's the cloud chamber come in? In a cloud chamber, the air is supercooled. The water vapor is more than ready to condense, so it does so at the slightest excuse. Even a cosmic ray leaving an ionized trail of broken atoms is enough. You can see the trail as mist, water droplets in air. If you think about it, there is an opposite to condensing. It is boiling. If we boil water, bubbles form. And like droplets of mist, they tend to form on surfaces. They need something to trigger the change from liquid to gas. Donald Glaser had the idea of using bubbles instead of mist to track particles. So that the liquid was more than ready to turn to gas and so make bubbles, he superheated it, the opposite of supercooling. He heated it, as one does with beer, in boiling oil. As with the cloud chamber, the superheated liquid will preferentially boil along the tracks of cosmic rays. So he had made a cosmic ray detector. In a cloud chamber, you're seeing tracks of condensation. In a bubble chamber, obviously, you're seeing tracks made of bubbles boiling. So the question arises, what causes bubbles? Bubbles are boiling hydrogen. Donald Glaser, who invented the bubble chamber, tried various liquid chemicals, also boiling them. He had glass bulbs full of liquid, which he cooled and then submerged in hot oil to superheat the liquid. Then he reduced the pressure with a piston, so the liquid was ready to boil. A particle passing through can provide what's called a nucleation seed to trigger boiling and hence a bubble, leaving a track. There's a story that Glaser had the idea from looking at a glass of beer. And in fact, he did try beer, but only as a liquid. And he proved only that lager is as good as water, which some of us who like real beer might agree with. But he eventually settled on diethyl ether and later liquid hydrogen. When he accepted the Nobel Prize, Glaser dismissed the wonderful beer inspiration story as fake news. It never happened. I despair of physicists and their quest for truth. If only they would sometimes leave us a romantic narrative. I mean, when they make the movie of the discovery of the bubble chamber, they're going to have him inspired by beer, aren't they? They won't leave that out of it. In fact, Glaser did try beer as a liquid for the bubble chamber. He just wasn't inspired by it. The fact that alcohol was not permitted at the university at Ann Arbor in Michigan wasn't so much a problem as that the chair of the university was a strict teetotaler and nearly fired him on the spot when he found out what he had done. And that is obviously going in the movie too. He tried the beer in secret at night, not because he feared the alcohol ban, but because he feared he might have been mistaken. Enrico Fermi, who was about as famous a scientist as one could find, had taken an interest in Glaser's work and discussed it with him and proved that Glaser's idea could not work. But luckily, Glaser was not entirely deterred by such an authority and eventually found a mistake in Fermi's work, corrected it, and showed that simple water could work. Thank goodness for physicists who don't believe everything they're told. The reason for trying beer was that he needed a liquid with low surface tension so that it could boil easily. And beer, because of the stuff in it, has a lower surface tension than water, but not much lower. And water is weird and has an especially high surface tension, so is about the worst thing you could use for a bubble chamber. And of course, he did use cold beer, but unfortunately then superheated it beyond boiling point in oil. In fact, he also tried ginger ale and soda water, as well as beer, but with a similar lack of success. So when I was young and I'd just finished my PhD, I was invited to a fellowship at CERN, where they study particle physics. Part of the reason for it was that I had studied cosmic rays with the professor who was head of department as an undergraduate student for my final year project. As it happens, I was recruited into CERN's instrumentation division, the one that makes the equipment, not does the physics. So my particle physics didn't progress. But CERN had a bubble chamber. It's a big bubble chamber. You can see here that the tiny figures are people walking around on it. It's a massive bubble chamber. That is a mega amount of hydrogen. If that hydrogen ever escaped, it would cause a huge flame. And so there was a big hole in the roof above it so that the flame would shoot out and not burn everything down. Luckily, it never did. It is a humongous bubble chamber. It is called the Big Bubble Chamber because particle physicists are really good at coming up with great names. The whole thing sits on a giant piston, and when the piston falls, which it does every few seconds, 4 fisheye cameras slam in to take pictures, then slam back out before the piston comes back up and crushes them, and then it does it again. It was really at CERN that I learned not just to use computers, but to make them, and more excitingly, to make them measure things and move things, which is called signal processing and control systems. And I loved the big bubble chamber because it was huge and it moved fast and it was controlled electromechanically. Later in life, I, like Donald Glaser in The Legend, was looking into a glass of beer. And recalling my love of cosmic rays and bubble chambers, I remembered that every second a muon was probably passing through my beer. Now, at this time, I knew nothing of the beer legend behind the bubble chamber, so I idly reinvented something that had been shown not to work. The serendipitous beer bubble chamber cosmic ray detector experiment. Might I, if I looked at enough beers, see a cosmic ray track in the bubbles? In a foaming beer, also, the foam would be like a photographic plate, a record of the track. So I'd only have to idly glance at the beer, not watch it like a hawk all the time. It seemed like a nice pastime for someone approaching retirement. And in that spirit, I decided not to work it out, not to calculate the nucleation energy needed to form a bubble in the beer. I would just see if it worked, and then work out the details later for fun. The experiment was serendipitous precisely because it was observational, as and when circumstances permitted, as far from a controlled experiment as I could get. As it happens, I was far from the first to think of the idea, and I didn't know that Glaser himself had ruled it out because of the anomalously high surface tension of water, even when moderated by beer. So when I finally checked Glaser's calculations to see if they worked feasibly for beer, I was disappointed to find that he himself had ruled out the possibility. But a whole warren of delightful rabbit holes opened up, only one of which is summarized in this talk. For example, in 1990, Frank Crawford at Berkeley used their Bevatron particle accelerator for a serious test of the cold beer bubble chamber idea. He, with colleagues, used the Bevatron to fire protons into a glass of beer, numerous glasses. In fact, because it turned out to be a long experiment. They ramped up the energy to 1,000,000 electron volts. Electron volts, the energy imparted to an electron by accelerating it across a volt. It's an incredibly high energy for a particle, but an incredibly tiny energy for us, about 10 to the minus 19 joules. And if you need more than 2,000 joules to boil a liter of water, so it isn't going to make many boiling bubbles. And nothing happened, or rather, nothing was seen. But they were diligent, so they carried on, increasing the energy and then using bigger particles. Eventually, they fired an iron nucleus. That's really big, at 600 million electron volts. That was the highest energy the Bevatron could produce. And they fired an iron nucleus every 4 seconds. Nothing. So that's disappointing. But a muon averages 4,000 million electron volts, not 600 million. The idea of beer as a cosmic ray detector that inspired Crawford is based on a mistake. It's a false legend that Donald Glaser was inspired by beer, and the true legend that he did try to use it. But he didn't try to use beer as we know it. He boiled it in oil. And his calculations are of the energy needed to boil beer, not to nucleate a bubble in a supersaturated cold beer freshly opened. Now, the process of forming bubbles in cold beer is definitely not boiling, not if it's served correctly anyway. Beer in a keg or bottle or can is kept under pressure. If it's real beer, the pressure is generated by carbon dioxide produced by fermentation. In some popular beers, naming no names, it is injected artificially. The pressure means more carbon dioxide is dissolved. When you open the bottle, the pressure drops, and there is too much carbon dioxide to stay dissolved. The beer is supersaturated, and the carbon dioxide comes out first, as with the cloud chamber and the boiling bubble chamber, where there are nucleation centers. In a beer bottle or glass, the nucleation centers are the glass surface. In real beer, there's also small organic particles in the beer itself. In lagers, those are filtered out, so the bubbles tend to form on the glass rather than in the body of the beer. And in real beer, there are surfactants that lower the surface tension and allow the foam to form and persist. Also, in bitter beers, there's nitrogen as well as carbon dioxide, and that also helps in forming the foam. And the foam, if you remember, is what I was hoping would record the nature of the beer. Be aware that beer glasses are specially designed. In many kinds of beer, the beer glass has tiny little sharp bits inside it, and those are designed to be nucleation centers for the bubbles so that the bubbles form a particularly pretty pattern as they go up the glass and as they form on the top of it. This is a good reason to use the correct glass for the correct beer. Also, the beer glasses are shaped so that there's a particular flow. A Guinness glass, for example, is shaped in such a way that the bubbles stream up the middle of the glass and then they stream down the outside of the glass counterintuitively, because you'd think the bubbles would float. In fact, they are floating, but they're floating up so fast in the middle that they're forcing the bubbles at the sides to flow down the sides of the glass. Beer bottle and beer glass design is an amazing treasure trove of the most incredible and difficult fluid dynamics and physics. So undaunted, we need to calculate the nucleation energy for a carbon dioxide bottle in cold beer, not to start it boiling. Now, Glaser's calculations were based on the critical size of the bubble that was created by the particle. The bubble has to be big enough to then grow to be visible. That depends on the surface tension, the temperature, and the partial pressure of the vapor. The details of the calculation turn out to be unimportant, though, because the only feasible way to get low enough surface tension and high enough vapor pressure is to get the liquid near to what's called its critical temperature, supersaturated, the state at which its surface tension drops to zero and it basically vaporizes spontaneously. And beer, when opened, deliberately basically holds itself near the critical temperature, not for boiling, but for bubbling. The bubbles are already almost forming, and the beer holds itself in that state for quite a time, as we can see from its continuing to bubble. But are the bubbles from cosmic rays big enough to see? Well, here again, beer helps us, because beer bubbles grow. They act as a nucleation surface for gas to enter and expand the bubble. The bubble itself causes nucleation. It's its own nucleation center. This is why beer bubbles grow bigger as they rise, and we are looking for them at the top of the glass. So there is hope. Interestingly, the standard explanation for why beer bubbles get bigger as they rise is completely wrong. What people say is that they rise because the pressure reduces, but a beer bubble in a normal beer glass almost doubles its size as it rises up the glass, whereas if it were water pressure, it would need to rise up 32 feet for that to happen, which is more even than there is in a yard of ale. What actually happens is that they act as nucleation centers. So the physics is more complex, but it's much more interesting. How big a bubble does a cosmic ray produce? Well, here's a crude example, thinking of it vaporizing water. None of these calculations make much sense. And feel free to check them, and I'm probably wrong. When I make a mistake, I make a big mistake. I'm a physicist, I'm allowed to do that. A typical muon has an energy of 4 giga electron volts. That's 4,000 million electron volts. To boil a liter of water takes 2,200 joules. So that is about 34 trillion typical muons. But we're not trying to boil a liter. The size of the bubble that a typical muon might create by boiling it, I mean, it's changing it from 100 degrees water to 100 degrees steam, might create a bubble about 60 micrometers across. That's 60 millionths of a meter. But Schaefer and Zare showed that beer bubbles start at about 1/5 of a millimeter. So that means we'd need about 3,000 times the energy of a typical muon to create a beer bubble, which is 12 tera electron volts, which happens to be the maximum energy that the Large Hadron Collider at CERN can generate. So for the beer bubble chamber experiment to work, CERN ought to be the site for it. And in fact, it may have been, because in 1996, the LEP, the precursor to the Large Hadron Collider, had to be stopped because it wasn't working. And it was discovered there were 2 Heineken bottles stuck in the beam pipe. And they never discovered who was responsible. But I like to think they were trying out the experiment. But our particle accelerators are puny by comparison with the universe. Biggest particle accelerator in the universe is the universe itself. In 1991, the Fly's Eye array in Utah, which looks at the sky to detect cosmic rays by the radiation that's emitted as they hit nitrogen in the upper atmosphere, spotted a cosmic ray with 320 exavolts of energy. That is 1,000,000 times as high energy as the Large Hadron Collider can provide. It would boil a bubble almost 1 millimeter across. And incidentally, if all that energy went into hitting your toe, it would be like you dropping a bowling ball on your foot. And how did they spot it? It left a vapor trail in the sky, which acts as a cloud chamber. Of course, that was a rare event. A black swan, if you like, serendipitous, using the sky as a cloud chamber. A couple of years later, ago, I gave a talk at another Café Sci about muons. Afterwards, a retired cosmic ray scientist came up to me and said he had a picture at home of an amazing cosmic ray cascade, the chain reaction that had been captured in the 1960s in a high altitude balloon and never published. And he offered to send it to me because it was interesting. This is the picture here. This is probably an incredibly high energy ion nucleus streaming in from the left, hitting the emulsion of a photographic plate and causing destruction as it goes. It triggers a shower called a cascade of secondary particles, pions and then muons. It is an amazing picture because it is like a miniature Big Bang, a very rare event captured. A particle, a cosmic ray, with an incredibly high energy captured by sheer chance where it happened to be. Now, if this had hit my beer, maybe I would have seen its trace. Unlikely, I grant. When I was at CERN, the Large Hadron Collider hadn't been made. We were surveying and tunneling to build the LEP, which years later, the Large Hadron Collider replaced in the same tunnel. At that time, the superproton synchrotron was the big accelerator, and it was being used in the hunt for the W boson, predecessor of the Higgs boson, which all that fuss was about. The Higgs boson, by the way, was called the God particle because it was like the key to everything. But it turns out, as with all particle physics, that the key to everything isn't quite the key to everything, and something else is that we haven't found yet. On the day the W boson was found, the place was electric. I'm ashamed to admit that I was by then so far from particle physics and so into computing and robotics and computerized instrumentation that I actually wondered briefly what, or even who, W was. But I followed the crowd and I squeezed into a balcony at the back of CERN's lecture theatre, which was absolutely full to capacity, to see Carlo Rubbia announce that the W had been found. It was a moment in science history, and I didn't understand much of what he was saying, especially when he went into equations. But I drank it in, and I still remember it with almost personal pride, although I played no part at all in it. I was just there, but that was enough. By then, bubble chambers were old hat. Electronic drift chambers, wire chambers, newfangled computer instrument thingies were used to collect and analyze huge quantities of data. The lady on the left here is manually marking bubble chamber tracks at a special trackball station the old way, and she was replaced by this time by automated computers, which would look for candidate events. Carlo Rubbia's team basically invented big data, humongous data, ginormous data, looking for rare events. They were looking for a rare event. W is not commonly seen. They knew what to look for. Just as we look for a straight track in our beer bubbles, so they knew to look for high energy electrons coming out at a large angle to the beam direction. That would indicate a collision producing a W boson, it then decaying to an electron or positron and a neutrino. You wouldn't see the neutrino because it hardly interacts with anything, but you could detect it as an energy imbalance. And that required a human to check the automated search. In the end, they collected data from 26,000 million collisions. In those 26,000 million collisions, they found 10 W events. Those events are rare, black swans. And maybe I need to drink 26,000 million beers to find my cosmic ray track. But the beauty of statistics is that however unlikely an event is, it is just as likely to be in my next glass of beer as any other one. And so I will continue with the serendipitous beer bubble chamber experiment, and I counsel you to do so as well. All you need for it is a glass of beer, or Prosecco, or sparkling mineral water, or Coke. And all you do is pour it into the glass and look at it time to time. And if you see a straight track, that would indicate a cosmic ray passing through it with phenomenal energy, nucleating a trail and taking us back to the original bubble chamber. If you do that, pictures or it didn't happen. Brocken spectres are rare. Brocken spectres with glories are even rarer. This is another one. This was taken by Michelle, who walks up Glastonbury Tor every single morning and photographs it. Because if you've seen one, you have seen a black swan. And with luck, you might see another. Thank you.
Right. Thank you for that. I'm just going to do my quick inspection for bubbles in my bubble chamber. But
I see there's a question, can I open my beer yet?
Yeah,
you certainly can.
I'm opening mine, so better be able to.
I can also say that I have opened my beer, but I haven't poured it out yet because I was so busy entertaining you all.
Okay, so Sarah says for the experiment. Yes.
Yeah. Sarah says, when you say hit something, do you mean anything like a person, a rock, or a tree? Or do you mean another atomic-sized particle? And that's an interesting question, actually, yes. I mean, yes, it hits something. Matter, material, humans, rocks, and trees, we're mostly full of empty space from the particle physics point of view. So there's almost nothing there except these tiny, tiny particles in the center. And so this is why the cosmic rays fly through us, because there isn't much to hit. It's an incredibly rare event if they happen to impinge on something like an electron or an atomic nucleus. So I'm really talking about it hitting an atom and knocking an electron off it, making an ionized particle, or hitting a nucleus and disintegrating that in a nuclear explosion. That would obviously be in something. the cosmic rays are dangerous to us because they can sometimes hit inside our bodies and then cause an ion to be created. And then that can go on and cause chemical reactions and cause cancer or mutations in our DNA and things of that sort. That's why astronauts are protected when they're in space and are not allowed to be unprotected for very long out there. So both are true. I mean, it hits something, but strictly speaking, what it hits is an atomic nucleus or an electron. And now she asked me, what temperature does oil boil at? And I don't know. You do, Sarah, because you're a cook. So you absolutely must, you must know the answer to that. I think it's well over 100 degrees at least. But I do advise people not to boil your beer in oil.
That. I can actually answer that one. So it will depend on entirely on the type of oil that you have. So for example, yeah, as Marion said, coconut oil is absolutely brilliant for this because it doesn't boil and it's got a very high smoke point, so it's great for making popcorn, whereas vegetable oil will boil at a much lower temperature.
Oh, there we go. It's perfect, isn't it? This is why we need a multidisciplinary approach to things. Oh, okay. So Sarah, we now get a question here. This takes us into an entirely different talk, so I won't answer it very well. Why are more bubbles released if you shake a bottle before opening it? Well, that's not quite talking about cosmic rays, is it? But it's interesting because the answers are very, very different, and some are right and some are wrong, but we don't know which. First of all, people thought that shaking the bottle causes what's called cavitation, causes a pressure wave to run down the bottle, specifically down the bottle. That pressure wave is like a shock from an nucleation. There's also a thing you can do called the beer slap, and I think it's more common in America than here. Luckily, I haven't got beer in this bottle, but if a bottle of beer has been freshly opened and is very cold and about to froth, what you do is you take your hand and you slap it hard. So it's called the beer slap. When you do that, it takes about a second or two, and then the bottle will almost explode with froth, a bit like when someone has shaken up a champagne bottle. And the beer slap's been studied with high-speed motion cameras because scientists are very serious about this kind of thing. And initially, that was thought to be the cavitation wave. So when I slap the bottle, I create a pressure inside it, and that pressure wave travels down the side of the bottle, hits the bottom of the bottle, and then travels back up again. And cavitation is when the liquid actually expands, so its pressure reduces, and the bubble is almost formed spontaneously in it. It's almost as if you took the liquid like this and sucked, and so a bubble forms in the middle of my hands there. That's wrong. And the reason that's wrong is that cavitation doesn't take that long. Cavitation is instantaneous, so the froth would occur almost before you removed your hand from it. High-speed motion photography and Schlieren photography, which shows the pressure wave, shows that in fact it's the motion of the bottle that does it. So it's not as complicated as the cavitation wave traveling down. What is when you shake the bottle, you move the bottle, and the liquid moves. The liquid then effectively touches more of the surface. The surface moves through it, and that causes the bubbles. So the whole surface of the bottle is acting as a nucleation surface, which is kind of interesting, isn't it? One of the problems with looking at beer bubble chambers, and especially learning about them, is that there's much more science about beer bubbles than there is about beer bubble chambers. And so you get lost in these rabbit holes of why beer bubbles do that and so on. And the beer industry are complete experts in how to create artistic bubbles that look good and last, and they feel good in your mouth and make the whole experience of drinking beer infinitely better. So we always need to use their own bottles and their own glasses for these things, because these people are the unsung heroes of the scientific world.
We have a question from Charmian. What happens if you use a shandy, and what about homemade beers? I can tell you that homemade beers can explode. Homemade blackberry wine does explode, particularly when you think it's gone quiet and put it in a wine rack. But if you're using a shandy, would the bubbles in that work?
Yes, they do. What Donald Glaser found in his rather extensive experiments, he tried loads and loads and loads of different liquids. And it's interesting because he was a brilliant man. He doesn't seem to have realized, or to have, at least not to have published, the idea that the beer is operating in a different way. He was looking for a liquid with a low surface tension and trying to make it boil. He wasn't looking at it as a carbonated fluid. I don't know if in those days beer wasn't bubbly. It's kind of weird, really. But it's like there's a gap, because people then went on to study the beer bubbles, but Donald Glaser didn't look like. He was a very interesting man, by the way. His invention of the cloud chamber resulted in these massive things like CERN, particle accelerators and everything. But his idea when he created it was that you could study cosmic rays on the top of a mountain like Ben Nevis. He imagined himself skiing in the morning and then going back to his little cabin with his small cloud chamber and studying cosmic rays. I guess he must have been absolutely appalled to find that people built enormous laboratories and buried stuff underground. In fact, he was, because he quit particle physics, went back to meteorology, and then went into this new field, which is quite important now, called biochemistry and biomedical research. So a fascinating and interesting man. What was I talking about? Shandy. Yes, he used all kinds of different liquids. Anything that is forming bubbles will act in the way that I think it does. That is, it won't work because it needs too high an energy, but it might if a big enough, oh my God, cosmic ray particle hits your beer. So the whole point of the serendipitous beer bubble chamber experiment was I didn't know if it would work. I was just thinking, if I look enough, maybe I'll see something and it would tell me it did, and then I could work it out. Now that I know it can't work, it can on incredibly rare circumstances. So anything with bubbles is acting almost the same. It doesn't matter what. But if you make a homemade beer or you make a shandy with a bitter in it, then you've got a different circumstance, because you've got nitrogen as well as carbon dioxide, and that changes the nature of the bubbles. The bubbles form more easily and they persist more, and they will be in the body of the beer. So if you look at my beer here, it's very good for the beer bubble chamber experiment because there aren't too many bubbles confounding the experiment here. Yeah? And they're forming a sort of light froth on the top of it, which I can see the particle tracks in. But a bitter beer would be fairly cloudy with the bubbles still, and the froth, the head, would be much thicker, so it wouldn't work as well with that. So anything that's bubbling is absolutely fine. And the funny thing is that beers and fizzy drinks are precisely engineered nowadays. Well, they were always invented and developed to maintain that bubbling. So it's as if somebody decided to make a liquid that is always in the critical state where a bubble is just about to form, and all you need is a cosmic ray to trigger it. Someone's yet to see it. I'm hoping someone does discover it at some point.
Right, we have one last question and a few minutes left.
Okay.
So from Betty, does anything travel faster than light?
No, in theory, not. I mean, the whole point of relativity is that the speed of light is the same whenever you measure it, however fast you're moving towards or away from the light source. And all the mathematics, all the experimentation that's ever been done shows that nothing travels faster than light. And the only thing that travels as fast as light is light itself. So anything with any kind of mass can't travel faster than that. Can I do the one about the best time to detect cosmic rays just before we close?
Yep.
So here, Lucy says, is there a best time of day to detect cosmic rays? What's the best time to pour my beer? Actually, there is, yeah, because the solar wind keeps cosmic rays away from us. So it sort of pushes them away from us, and that blanks us a little bit. So in the evening and in the morning are the worst possible times. The best times are in the middle of the night, when the solar wind is completely obscured, shadowed, if you like, by the Earth, and then cosmic rays are common. And in the middle of the day on a sunny beach, because then you've also got the solar wind, and it's just possible that the sun might produce an alpha particle energetic enough. So I would suggest that in the middle of the day in sunshine is really good, and in the middle of the night, if it's a clear night, is also good. But in the evening or in the morning, just drink the beer and be happy with that.
Thank you. Right. perfect timing because we've got to head to the pub soon. But thank you all for coming. I'm just trying to remind myself what the next one we have is, because obviously we are
I know
running
it
these.
was going to be poetry of science, but unfortunately Sam's had to pull out of that due to parental
parental
duties.
responsibilities.
I think we have comic strip science.
I think we do. I'm just checking the date on that one. So we do have comic strip science definitely coming up, and that will be on
8th of April, from memory.
Well, you got there first, but
I did. And then May, we've got Helen Sharman. So I'll be in conversation with Helen Sharman, Britain's first astronaut, and we'll be talking. She wants to talk about space and Mars. So we'll talk about that.
There's a fair chance we'll have a few other things pop up before then.
Yes.
Couple more very quick questions. So can you do these in about 5 to 10 seconds
sure.
each?
Of course I can.
What happens to the bubbles if your beer's in a cask, not a glass bottle?
The same thing will happen, but you won't see it. It's quite interesting, actually. There's just quickly, right? A cosmic ray energetic enough to trigger a bubble creation in my beer is going incredibly fast with incredible energy. So it has to be massive to be able to do that. However, to reach my beer, it has already demonstrated that it can pass through about 20 kilometers of atmosphere without interacting with anything. So there's a bit of a contradiction here. In order to hit my beer, it has to be ready to hit something. But it's already come through an incredible distance without hitting anything. So it's absolutely totally resistant to interacting with anything. And it's more than likely to pass straight through my beer without even seeing it. So that's quite interesting. And if you're in a cask, then it's had to pass through the wood of the cask to get into it. And I don't know if wood is more difficult to pass through than beer. It probably is. So it would stop or slow down some things. However, if a sufficiently energetic particle hit the cask, as it does with the glass, it might then trigger a cascade. And so you might then get a surprising stream of bubbles inside it. But this has never been seen. And looking for beer bubbles in a cask is looking for a black swan in an opaque container, so it might be even more difficult.
And from Lucy, are there likely to be more cosmic rays detected on Mars? Should NASA have given Perseverance a beer to take with it? I mean, I'll say that would probably have helped with the name. Certainly helps me persevere.
Yes, absolutely. There aren't likely to be more cosmic rays. There are more likely to be more cosmic rays on the surface of Mars, more primary cosmic rays. So actually, yes, it'd be a great place to take a beer because you're much more likely to be hit by a massively energetic iron particle on the surface of Mars. But there are more muons because the cascade creates a lot of particles. And so there are many more muons than there are primary cosmic rays, but they're less energetic. So yeah, Mars for seeing the really big ones on the surface, but the surface of the Earth for seeing little mini ones, but more of them. You get about 1 per second passing through a glass of beer down here, whereas probably 1/100th of that of the iron nuclei that trigger the cascade up on Mars. So you'd have to wait longer for your beer on Mars.
And finally, from Marion, when I've seen a straight line of bubbles in my beer, have I seen an oh my God ray? Some have been about 3 centimeters long.
According to the criteria I set for myself, yes. And I have never seen a totally straight line. So my idea was the cosmic ray is traveling in a straight line. It's undeviated, and therefore I will see it as a straight line. The true test of that would be to put a powerful magnet under your beer, because then the cosmic ray would actually curl round a little bit under the influence of the magnet, and then you could prove that it was the straight line. But yeah, Marion's probably seen my cosmic ray straight lines, unless there's something like a needle lying in the bottom of your glass or a scratch.
What in fact you're saying then is that there is potential for a Cafe Psi themed beer stein with a strong magnet in the bottom.
I think so, yes, actually, that would be good. Yeah, definitely. That's a patentable idea. We'll have to do that.
Okay. So, yes, thank you all for coming. The next one is on the 8th of April and will be on comic strip science or science comic strips, one of the two. The next scheduled one after that is May with Helen Sharman. I'd give it at least a 50% chance we'll probably have one or two between now and then. So watch this space. And I am going to end